video? Thank you. Thank you. Right.
Right. No.
Okay, so I clearly rushed towards the end on Friday when we started to talk about superconductivity. So let me just sketch what we discussed, and so that we can actually talk a little bit more about it. So one thing we did is that we know now we're talking about a field which should represent two annihilation operators in the ground state, because that's the pairwise condensate we have in superconductor, P and minus P. And we know then that this has charge 2e and mass 2m, because it corresponds to a pair of electrons. And in practice, because the electron is moving inside the medium, sometimes it's actually more difficult to move. It acquires more inertia. So this mass actually ends up being a lot larger than the mass of the electron in the vacuum. And in some cases, it can be even thousands of times heavier than the mass of the electron outside the medium. And that kind of system is called heavy fermion system. So these things can happen too. So when I write mass, it may not precisely mean the mass of the electron in some systems. So that's something you need to be aware of. But for the midterm problem, of course, please use just the mass of the electron, because I'm not asking you to do anything else. But the point here is that this is the only piece of information we have, and we are trying to write down the Lagrangian for this composite field psi. Because it describes a composite object made up of two electrons. And then we have this principle. Now let's impose Galilean invariance and gauge invariance. And we talked about gauge invariance the last time. So when you have electric field manipulation, when you have electric magnetic field. We have written this last time, so if we have done it, you don't need to do it again. We have electric field written in terms of scalar potential and vector potential. It's time to protect. Magnetic field is the curl. And when you change phi to phi prime, this is again time derivative of some function chi. Chi depends both on space and time. And vector potential to this prime one. The gradient of chi, the electric and magnetic fields don't change. But when you do this, to preserve the form of the Lagrangian, we also need to change psi, field psi, to psi prime, which is given by this phase, which is the same function that appears in the gauge transformation of the scalar potential and vector potential. So if you do all of these at once, then the Lagrangian made up of phi, a, and psi turns out to be exactly the same thing as the one given by the primed object. So that is the invariance of the field. If you do all of this above, then the Lagrangian doesn't change. Therefore, that is the gauge invariance. And the idea of imposing this, as we talked about the last time, is that electric and magnetic field is something you can measure. So they are clearly observables. But when you write electric and magnetic field in terms of scalar potential and vector potential, then writing it this way was not unique, because you can change phi and a in this fashion based on the same scalar function chi without changing electromagnetic field. So this change should not affect physics at all. That is, in some sense, the artifact of using scalar potential and vector potential, so the physics shouldn't change. And when you demand the physics shouldn't change, we like to see the Lagrangian and Hamiltonian don't change. But in order to achieve that, in the presence of this charged field, you also have to do something in the charged field at the same time by changing the phase of the field locally, differently from one place to another. So you change the field here by, let's say, phase 2/3. Here you change the phase by one half. And depending on where you are, you can change the phase of the field arbitrarily from one place to another. But as long as that phase change is accompanied by this gauge transformation on scalar vector potential, Lagrangian doesn't change. So that's one thing we have to impose, because phi and A, in some sense, are fictitious degrees of freedom. And that is what is often called redundancy in description. And at the same time, we want the system not to depend on the reference frames. And in the case of superconductor, of course, there is a rest frame. It's sitting inside some metal or something. But if you apply the same idea to, for example, just a gas of helium-3 or something, then clearly it doesn't depend on the reference frame. So at least to a good approximation, we can demand the Galilean invariance so that the physics doesn't change from one reference frame to another reference frame where you're moving. And I asked the TA to talk about this tomorrow, so hopefully that gets covered. But the idea is that your field, xt, transforms to something a little bit complicated. So here we have mv dot x. This v is the difference between two reference frames, from one reference frame to another. So you put in this phase factor together with, of course, change in the position, because now you're moving. So if you're moving and sitting in the train, the other train that is not moving looks like it's moving the other direction. So the position of the other train moves in the opposite direction, hence x minus vt. But this is not relativity, so the t is common to everybody, so time is common to everybody. So we have to demand that the Lagrangian doesn't change under this transformation either. The tricky thing is that here is x and here is t, so when you have derivatives on the field, then it can pick up some stuff from the phase. In order to actually avoid that, it turns out that you can define only one type of derivative. And if you use this combination, then d has time derivative inside, and psi prime now has time derivative inside. Psi prime. So in addition to derivative acting directly on this original field psi, together with this complicated phase factor, you can also hit time derivative in here. That will give me half mv squared over h mod psi. And you can also hit the spatial derivative x over here. That will put out mv squared. But when you actually look at this piece and that piece precisely cancel. So only when you have this combination of this first order time derivative and second order spatial derivative, the whole thing ends up transforming to just a phase factor. an original field with this same combination of derivatives. So what that means is that when you write a Lagrangian, you always have to combine derivative in this form, which changes by a phase, and you need to have equal number of psi, so you can actually build your Lagrangian based on field itself, derivative with this combination, twice, third, and so on. So these are the building blocks you can use. In the same way, they come with conjugate. And all of them changes by this phase. All of these would change by their complex conjugated phase. Then you can build a Lagrangian only when you have equal number of psi and psi dagger so that their phases would cancel. So that means invariant Lagrangian contains pieces like psi dagger psi. We have looked at many times by now, chemical potential. Psi dagger psi psi. That's the interaction term we looked at before. You can also have psi dagger deep psi. That is the Lagrangian we already had. But in principle, you can also have terms like deep psi dagger deep psi, deep 3 psi dagger d to the 4th psi, and you can even multiply by the psi dagger psi. As long as you have same number of psi and psi dagger in every term, and if the derivatives come only in this combination d, then you'll guarantee that this is an invariant Lagrangian. So because of this property, that this derivative would make the field change in the same way as the field itself does, this kind of derivative is called covariant derivative. So when you have this form of the derivative of the field, the whole thing changes in the same way together with the field itself. So co means together, variant means changes. So this derivative would let the final product change together with the field itself, hence covariant derivative. So that's the tool we have in building Lagrangian consistent with the Galilean invariance. Yes?
Do you have the same number of the d dagger and d?
You don't need to. But we already know that we need this term, right?
Yeah, what?
So here I have only one d acting on psi, but no d acting on psi dagger. No matter how many d's there are, this combination still changes by the same phase factor. This one also changes by the same factor, complex conjugated. So this whole thing is invariant. So this is allowed. You don't need to have the same number of d's acting on psi and psi dagger. But you still need to have the same number of psi's, 1, 2, and psi daggers, 1, 2, so that the phases all cancel against each other.
Okay.
Did I answer your question? Okay. So that's the idea. And it turns out that you apply the same idea for the gauge transformation. Because when you change the field by this phase factor, and when you consider spatial derivative acting on it, not only does spatial derivative can hit psi, but can also hit chi in the exponent and pull out grad chi. Then it looks like the psi doesn't change the same way as the original. Psi prime doesn't change the same way as the original psi. But grad chi is something that appears also over here. The vector potential changes also by grad chi. Because of that, you can again take the following combination. If P is which I call capital D vector. And when you take this combination, this acting on psi prime as e to the IE chi of h4, d psi. But this derivative can also hit the exponent here. And inside this D, so this D, because it contains A in it, when you change psi to psi prime, you also need to change D to D prime. And that contains the shifted A in it. But shifted A is grad chi. And this is also grad chi. So they again cancel against each other, so that the whole thing ends up being just a phase times the original derivative. So again, we call this covariant derivative. Because this derivative after gauge transformation turns out to be everything before the gauge transformation except for this overall phase factor. In other words, whenever you have the spatial derivative, you always need to pair it up with the vector potential to make sure that the whole derivative transforms just by a phase factor. So once you know this, you can write a term like this. And then after gauge transformation, everything is changed to prime object. But after the gauge transformation, the only change for this combination is by a phase factor. This changes by a phase factor. That changes by a phase factor. So in the end, the phases cancel. So that this combination doesn't change. The same idea. So whenever you have a transformation that involves the change of the phase of the field, in order to build a Lagrangian that's invariant under that symmetry, you have to make sure to combine derivatives in particular fashion so that that derivative as a whole would only lead to an overall change of the phase of the object. Then you know how to write down terms in Lagrangian that respect that symmetry invariance. Any questions about this? Yes, Andrew.
I do have a question about the 2 at the exponent there. First, before that one, exactly. There is the 2 at the exponent.
Okay. So here I was thinking about this Cooper pair field, that's why I had 2.
Okay.
And but in general, when you have a field with charge E, and this is what you do. If you have the field with charge 2E, then you have to put 2 everywhere consistently.
Okay. So which one is the gauge invariance? Like which one should we use the 2 or shouldn't we? Like when should we use the 2 and when shouldn't we?
When do we what?
When should we use the 2 and when shouldn't we?
So it depends on what this field is meant to describe.
Okay.
So if that psi is meant to describe something with charge E, then you don't put E there.
Okay.
Right now, when you talk about superconductivity, psi is supposed to describe Cooper pairs.
Okay, okay.
So that carries charge 2E, then you consistently use 2E
Oh,
everywhere.
Okay, it's because of the charge. Never
Yeah,
mind.
so once you know what field is meant to represent, then you know exactly what factor you're supposed to put in there.
Okay.
Thank you
Sorry.
for asking. Any other questions? Yes, Sarah?
It's also related to what you asked previously, I think, but I don't understand why we can only have one G, because I thought to make the Lagrangian invariant, we want to have 2 phases cancel out, so if we want to have a phase from just the psi term and then a phase from the psi dagger term, then I would think we need at least both of them having D acting on it.
Okay, so Does this answer your question? So if I have a term I wrote up there, side angle deep side, then this D and the whole thing is an inside spatial integral. So as usual, I'm allowing myself to do a integration by parts. So this d derivative x on psi plus psi dot. And if I allow myself to integration by parts, this the graph would work on the psi dagger instead. Then I get the minus sign. Then it does have two powers of spatial derivatives. So that is what ends up being p squared with 2m. In momentum space, this is what ends up being energy. So you find the usual kinetic term for the free particle. Does that answer your question? Or maybe you're asking something different.
Yeah, I was asking, we want the phases to cancel.
Yeah.
Right? Then do we not need D acting on psi and D acting on psi dagger at the same time? So
Okay.
Why do we not have to have the same number of D's?
So point is, psi under Gaussian transformation changes by this complicated phase. At the same time, deep psi also changes by the same phase. That was the whole point of covariant derivative. And psi dagger changes this complex conjugated. So even if there's only one derivative here, if you write this combination, it changes by this phase complex conjugated times this phase, so they cancel against each other.
How do we get that? How do we get that phase? How do we get that phase factor?
Yes, sir?
How do we get that phase factor in front of the psi dagger?
So if I write this out, then that's mvx mv squared d over h bar. Then I have minus mvx over h bar plus mv squared d over h bar. Because this is psi dagger, so it changes the opposite phase by this one. And then this phase is the same as that one. That was the whole point of covariant derivative. And this phase and that phase are opposite. So this phase and that phase are opposite too. So they cancel. So that this term is invariant under the Gaussian transformation. You don't look happy.
I don't know why I'm so confused, but I just don't get why we can get the phase without psi dagger having D.
So your question is about this one then?
How do we get the phase in the bottom line without having the covariant derivative acting on it?
Because this is just complex conjugate of this one. Psi changes by this phase. Psi dagger changes by the opposite phase.
Okay. Okay, maybe I understand now.
Yeah, so the whole point is that psi changes by the phase, psi dagger changes by the opposite phase. That's the beginning. But the point is that whenever you add this D in that particular combination, no matter how many times you add D on it, the whole thing still changes by the same phase as the psi itself. And again, with psi dagger, it doesn't matter how many times D you add D on it, but end result is that the whole thing also changes by the same phase as the psi dagger itself without derivatives. That's why you can build invariants just combining psi with some number of derivatives, psi dagger with some other number of derivatives, as long as in the end you have the same number of side and side dagger in a given term in the Lagrange.
Okay.
So I'm telling you here that it's the same idea for the gauge invariance. And not only that, you have to take care of the spatial derivative when you do time derivative. This will also pull out time derivative of the space vector chi, but chi dot appears precisely in the change of the scalar potential phi. So it turns out that when you actually put in this scalar potential together with the time derivative, then dt prime phi prime again changes by the same phase vector. So this is also covariant. So end result is that whenever you want to write derivative in your Lagrangian, spatial derivative always need to come in combination with the vector potential. Time derivative always need to come in a combination with the scalar potential. And because of the Galilean invariance, the time derivative and spatial derivative need to come in this particular combination. So end result is that I replace this one by dt up there, and this one by d up there. And then you can use only this combination to write down your Lagrangian. So what you can write in your Lagrangian becomes very limited. So clearly, if you start with low orders in derivatives, things like this is clearly allowed because the phase change in side and side dagger always cancel against each other. And you end up integrating over x. So if you do Galilean transformation, this changes to side dagger x minus bt, side x minus bt. But x is a dummy variable for your spatial integral, so I can change x by vt everywhere. And therefore Lagrangian doesn't change. And you can do the same thing. That's the interaction term we already looked at, so that's allowed too. So the only non-trivial thing now is that when you include derivatives, time derivative always need to come together with the scalar potential. But time derivative also needs to come together with the spatial derivative. But this spatial derivative needs to come together with the vector potential. So in the end, you have to write a term that looks like this. Having this time derivative together with spatial derivative squared guarantees the whole thing is Galilean invariant. The fact that time derivative always comes with scalar potential guarantees it's gauge invariant. Here also, the spatial derivative comes with vector potential guarantees it's gauge invariant. And that's the Lagrangian you're supposed to use. And in principle, you can start writing higher orders in derivatives. You can stick in more powers of psi in here, and so forth. But to the extent that you're looking at the phenomena at long distances, low energies, then stopping somewhere with rather a few number of derivatives is always justified. In power series in energy and momentum. And if you're asking questions like superconductivity, then you want to make sure that it satisfies Landau criteria. You're only looking at the very low energy phenomenon, which is happening over here, and draw a line V down to V. So energy is always small. In a typical superconductor, we are talking about millikelvin, instead of typical energy of electron in electron volt range. So this is actually tiny. So typically, you don't need to do any high orders in that energy, which is already tiny. You're also looking at some macroscopic phenomena, where, for example, current flows through the superconductor, then you see very little spatial variation in the phenomenon, which means that momentum is also low. So you don't need to worry about higher powers in momentum. So typically, we stop here and don't write any higher order terms in derivatives. So these terms don't contain any derivatives. We make sure that they are Galilean and gauge invariant. But with these terms alone, nothing moves because there is no derivative. So we better have at least some term that contains derivatives in it. And this is the lowest order term which contains derivatives you can write, consistent with the order symmetries. Then, once you have this term, then you can typically forget about higher order terms in derivatives, and you stop. So that's how we know, even though psi is meant to represent this composite object made of two electrons, this Lagrangian is the one you want to look at. So that's the argument I given the last time on Friday. So the modern view of how quantum field theory works is that you think about what symmetry the system has, then start writing Lagrangian consistent with that symmetry to some order you need in expansions in powers in derivatives. And typically, lowest order terms you can write down would suffice to most purposes. And then you say this kind of Lagrangian is effective field theory. And I know Kate raised her hand, so let me get to that. So this is field theory, obviously. But we call this effective field theory because in some sense it's some kind of low energy approximation of the field theory consistent with all the symmetries you have in the system. So that's the spirit. So whenever you write down the Lagrangian quantum field theory, we sort of build up from creation and annihilation of every particle at every position in space. That's how we came up with this kind of Lagrangian. But now we have a also top-down point of view. That once you know the symmetry of the system, you know what terms you are allowed to write in a Lagrangian. That turned out to be exactly the same thing we have done from the very beginning. So everything matches up. So bottom-up argument of building QFT, that's the way we did it in this first half of this course, turns out to be exactly the same thing of top-down point of view, that you start with the symmetries and write out the Lagrangian consistent with the symmetry. So that's how everything actually ends up making sense. In this point of view, of top-down point of view, turns out to be more important starting in a week or so, where we actually use relativity and write down Lagrangian consistent with the Lorentz invariance. So in that case, Lorentz invariance is so important that you need to know ahead of time, we want to write Lorentz invariant Lagrangian. And knowing that symmetry of the Lagrangian, then you write down whatever you are allowed to write to get started with talking about electromagnetism, Dirac theory of relativistic electrons, Clyde-Gordon theory of the relativistic spin zero particles, and so on. So symmetry first, Lagrangian next. We did it the other way around in the beginning of the course, just because of that's sort of a better way of connecting to what you are familiar with, namely quantum mechanics. That's why I did this way, from bottom and up. But modern view of QFT is actually top down. You identify symmetries, then you start writing down the Lagrangian consistent with the symmetries. Okay.
Yeah. So when will say the second order covariant derivative for the invariant Lagrangian comes into play?
Yeah, so you can actually, for example, put this whole thing squared. So that's again consistent with the covariant derivatives. Time derivative with spatial derivative come in combination. Every time derivative comes with scalar potential. Every spatial derivative comes with the vector potential. So if you put this whole combination squared in the Lagrangian, you're allowed to do that too.
But, because we've written down the invariant Lagrangian with combinations like at the very low, yeah, we have all these allowed.
Right, all of these are allowed.
Yeah, but I cannot identify, like, for example, the closest, the ones closest to you, like D side dagger. Yeah, this one.
Ah.
That will disappear.
So
or
this is
can I
also
see-
allowed. So sticking in square is this one.
Yeah.
But again, using integration by parts, I can let 1 power of the whole thing act upside down instead. Then it's the same thing as this term. So what I'm saying is that this thing is the same thing as psi dagger the squared side by integration by parts.
So when it comes to, say, third dimension, no, not third dimension, third order.
Third
then I
order.
can also like triple the time.
Yeah, that's right, yeah, yeah.
Okay.
So you just take arbitrary powers here of this whole combination, and you should stick to this particular combination to make sure it works out with the symmetries.
Mhm.
But as long as it is written in this combination, you can put arbitrary powers you want.
I have another question.
Go ahead.
So we talked about top down, right? This is top down. But I don't, like, because when we do the bottom up, it kind of seemed very natural to me. But can you simply talk about how is the bottom up, like the whole procedure? Because in the top down, we know the asymmetry, Lagrangian, and then with some conditions, and then we write down the Hamiltonian and all that. But
So do you understand your questions? So at the beginning, we try to do everything bottom up.
yeah, bottom up means I did it, but I don't know what exactly is the standard procedure for bottom up.
Yeah, so what we did bottom up is that we actually secretly had Galilean invariance in it,
Uh-huh.
because we made sure, starting with this field on the lattice, we made sure that in the small lattice spacing limit, energy turns out to be p squared over 2m. And there was some correction that went like 1 minus cosine something, right, if you remember. But we made sure that this would come out. We chose parameters to make sure this would come out. And once you actually impose this, that's basically the combination over here, and energy goes like p squared over 2m. So the fact that we actually insisted on this one in bottom-up approach, secretly, we have imposed the Galilean invariance already. So that's why this bottom-up approach we have done at the beginning of the class turned out to be the same thing as imposing Galilean invariance from the top, because that meet with the same behavior that free particles should have the kinetic energy of p squared over 2m. So it probably sounds too miraculous. Why what we did at the very beginning in a very heuristic fashion turned out to be right at the end of the day. But the crucial factor is just simple idea that the kinetic energy of a non-reduced particle is p squared 2m. And that, in the end, ended up imposing Galilean invariance on the final form of the Lagrangian. So that's why, it looks miraculous, but there was a reason for it.
Thank you.
That's an excellent question to ask. Any other questions? Does it make sense? Okay. Now that we have the Lagrangian, then we can use it. And just like in the case of BEC, we are talking about macroscopic quantum phenomena now, which can be written in terms of classical fields, again, the particle wave duality. So in the end, all you have to do is to solve this Euler-Lagrange equation. And I forgot the other terms. Plus sine, sine. And the easy thing to do is when you don't have external electromagnetic field, then this is exactly the same Euler-Lagrange equation for the Einstein condensate. You have dealt with already many times in your homework problems now. Then we know its simple solution. The first thing is just the mu over lambda. That's a static condensate. Second solution we looked at and you have verified that this is also a solution to Euler-Lagrange equation. And this might look like, okay, where did it come from? It looked like it came out of the blue, but now you know. This solution was just a Galilean transformation of this constant to a moving frame. And I made a mistake here. So this is x and t independent, so this is just a constant as well, together with this overall constant. So this is the solution, sorry. So once you solve the equation in the rest frame, where you ignore all the derivatives, just minimize the potential to find this solution, that's easy. And once you find the solution, you just go to another reference frame, moving this speed v, and we have learned how to do that. And there we go. And then this is guaranteed to be a solution of the Euler-Lagrange equation in this frame as well, because your system is invariant. Under the Galilean boost, we made sure of it. So if this is a solution in one frame, then this one in another frame must be a solution too, and you plug that into the equation and verified it. So in some sense, this is not a surprise. You don't need to work hard to come up with a solution. Once you know this, you automatically get this solution as well in just going to another reference frame. So this represents a piece of superconductor in our context, and this represents a supercurrent. And you have worked out current density with this solution too. So you worked out that this is actually really showing the flow of the particle, then the condensate. Now what we have to do though, of course, whenever you see a derivative, you have to promote this to a covariant derivative. But because we are now looking at the case where you don't have the external magnetic field, then there's no difference. So you once again find this current density to represent the overall flow of the entire condensate. So the electric field, so the electric current can flow through a piece of superconductor using this solution. Any questions about that? Everything okay? All right. Yes.
Why you say there is a Galilean transformation between that side and that side, and why is this Galilean transformation have both the phase shift in space and time? I think.
Why you need a space factor?
Yeah, I think there are two different parts. One is shifting through time, and one is shifting through space, right? And I think, as I know, as I understand, I think Galilean transformation just changes the spatial part.
So the x minus vt, I lost it somewhere. That's right. So if you have psi here, it should go to x minus vt.
Mm-hmm.
But in our case, psi xt was a constant. So even if you put in x minus vt and t into a constant, that's still a constant.
Mm-hmm.
So that's why I didn't have x minus vt in this function, because I started out with a constant. So psi of xt is this constant, so that I can solve this equation.
Mm-hmm.
If I stick in x prime minus vt t into this function, because this function does not depend on x and t, it doesn't depend on this argument at all, this ends up being the same thing as square root mu over lambda.
Yes, I understand that.
So this piece is psi of x minus vtt actually.
Okay.
So if I had written this on this side, then that's the same thing we're talking about over there. Maybe not over there. Where did it go? What I'm trying to say is, so that's the combination we want, right? Psi prime. And I have this space vector here, and I have this function. But this function we knew was just a constant.
That is a constant. I
Yeah.
understand that. But my question is, why the Galilean transformation includes the exponential, both the spatial part and the time part?
So the question is, why do we need the space vector?
The time factor, the part including time there.
You're talking about this?
Yes. Why this vector includes two parts?
For mathematical consistency. So I hope that the GSI will tell you that what you have to do is to actually think about sort of a series of transformations. Again, this is something we need to think about when we go to relativity, but Galilean relativity is that you have the system, then you can actually move the system, then nothing changes. You can rotate the system. It's a 3x3 matrix. Nothing should change. Then you can also go to this moving frame. Nothing changes. And also, when you actually think about time, shifting time should also not change. The system, the spatial translation invariance, spatial rotation invariant, Galilean boost invariance, time translation invariance, and you have to consistently deal with all of these symmetries which we normally take for granted, but in a consistent fashion. Then it turns out that when you actually want to make sure that all of these things work on the field consistently, in this case, psi of x simply goes to psi of x plus a. In this case, psi of x goes to psi of this rotated position. But if psi carries some spin, you need to also do some spin rotation matrix on top of here too. And this is the Galilean transformation we just talked about. This is just going from psi xt to psi xt plus tau. So when you think about this Galilean boost, you have to make sure that that respects all of the other things at the same time. Then it turns out that you have to put in this particular form of the phase factor in the end. So that's what I meant for mathematical consistency. In order to have all of these symmetry we take for granted for non-relativistic systems, then it turns out that this is the only way to do it.
Okay, I understand this part. Now my question becomes, how do I understand that the original psi, it seems like it's just a constant function, right?
Uh-huh.
It doesn't oscillate through space nor time.
Hmm?
Then how do we just by employ a Galilean transformation, then suddenly it oscillates through space and time? Because originally it doesn't oscillate at all.
So at least intuitively, I hope that makes sense, because this basically shows a plane wave.
Yeah.
What used to be constant is now a plane wave by
Why?
going from rest frame to a moving frame.
Mm-hmm.
So at least that's consistent with that intuition, right?
It kind of doesn't make sense to me. Because originally, if in my frame there is no oscillation at all, it's
Right.
constant.
Right.
Then in your moving frame, you kind of looking at it and it's a wave.
That's right, it's a wave, yes.
And that is Galilean transformation.
Yes.
Oh.
But that's how it should be, because if something is moving relative to you, it should like a plane wave.
Okay, I'll sort it out.
Okay.
It's weird.
We can keep coming back to this point. So now we have this Lagrange and we know how to use it. So now let's look at something that's a little interesting. It is something we talked about the last time. Here you have a piece of superconductor. You apply magnetic field, and you ask the question, what would happen on the edge of the magnetic of the superconductor? And for this purpose, you have to write down the Euler-Lagrange equation together with the vector potential. And to actually look at this equation, then you need to add also this piece of the Lagrange as well. For the electromagnetic field. And here, the constant some of you were looking for. And then we're looking at the case when you have a constant magnetic field here, so I don't need scalar potential. I only need the vector potential. And writing the Euler-Lagrange equation together with this one and that one, then you find basically Maxwell's equation. This is the usual Maxwell equation or Ampere's equation. If there's a current flowing, then you create magnetic field around it. But we have learned that this current is given by this. So this is just plugging in the current out of the scoop of your field. And the way you can obtain this equation is by taking variation with respect to A. So this term is curl A. You take a variation, and then you let this one act on this one by integration by parts. Because this is B, you let this curl acting on B by integration by parts. That's how you get this curl B. from the variational principle. In a way, you get this one. It's looking at Lagrangian. Lagrangian looks like this. By taking variation with respect to A, then I get the first power out of this derivative. And that's the power here. And because I have two factors of A, out of two derivatives, I can take variation from the second one. In that case, it's acting directly on psi. The other derivative should act on psi dagger. That's this term. If I take variation from the second derivative, then this derivative, the other one, is remaining directly acting on psi. No derivative acting on psi dagger in this case. That's how you get this term. So this whole Maxwell's equation arises also from the minimal least action principle, just by taking variation of the action relative to the small variation in vector potential. So that's how you can obtain this equation. And then you plug in this constant psi in here. And then inside this D, you have the D minus H bar over I to E A. So this derivative is now coming together with the vector potential. I factored out H bar over I from the combination. And this derivative acting on constant vanishes. The only piece that remains is this vector potential piece. So H bar over I over H bar 2EA, and this is constant psi dagger psi. A squared mu over that. And A. There's a factor, that's right, because I have this term and that term. Thank you. So times 2, so this becomes 4.
That is true because you have the A2F.
So thank you again. There's a 2 downstairs, 2 upstairs, they cancel, and the other factor 2 over here, so there's a factor of 2. Thank you, Jeff. And let's see, and also if you take the Coulomb gauge, and write out this combination over here, this turns into just write the curl of curl, just a vector calculus, and Coulomb gauge, this vanishes, so the only thing that remains is here. So in the end, you find this equation, which is called the London equation. It's not that somebody was living in London. London is the name of a person who came up with this equation. And using this equation, I told you last time already, and you're looking at it in a midterm problem, that you can easily find a solution where vector potential going into x as a function of this depth is given in terms of vector potential at the surface with this exponential factor, where lambda L squared is given by inverse of this combination. And this is actually the number density. And I believe that's the combination you found. I'm missing still 1 power of E. So this is the current density, but what we need is electric current density. And because this field carries charge 2e, that's the factor I forgot. Sorry about that. So here I need to put a factor of 2e, factor of 2e. So this actually makes it 4e squared. 4e squared. And that's the combination you're looking at in the first problem of the midterm. So, as a result, the magnetic field damps exponentially into the superconductor. And this is actually very strange, because we know magnetic field is a long-range force. Compass in your hand points all the way to the magnetic North Pole. So it acts over the distance of the size of our planet. But inside a superconductor, magnetic field becomes short-range. In other words, when you have a piece of superconductor, if you apply magnetic field on it, then it gets repelled. Doesn't get inside, except for only the skin of it. And this is what is called the Meissner effect.
Well, we also noted for normal conductors we don't have any electric field in it, so I mean it makes sense.
Say it again?
Like we also noted for like normal conductors,
Uh-huh.
we also don't have an electric field in it,
That's right.
so it makes sense. I mean it's nothing.
Oh, I see. So you're saying that this is similar to electric
Yeah.
field in a conductor.
Yeah.
But for magnetic field, magnetic field does get into the normal
Yeah.
conductor though.
Yeah, yeah. And this is this is the magnetic
Right,
field.
right.
My bad. Yeah, for sure.
So the electric field doesn't get into it either because it's a superconductor, so better than conductor. But magnetic field doesn't get in either,
Okay.
and that's the new part.
All right, thank you.
And this is probably something you might have heard about, or might even have done in the laboratory. That in some cases, magnetic field can also penetrate in a way that's really squeezed into these narrow tubes. And that's the last subject I'd like to talk about. I briefly mentioned that last time, but something I'd like to talk about now. But any questions about this? So everything follows from the same idea. The minute you have Lagrangian, you can do a lot of things. Now, by adding this term for the electromagnetic field together with Lagrangian for the Cooper pair field, then you can take the usual way of deriving the Euler-Lagrange equation by taking small variation with respect to vector potential in this case, and demand that vanishes. That gave us this equation with factor of 2e, I forgot originally. And if you write it out, in the presence of this condensate of the Cooper pair, you find this London equation, which tells you that magnetic field is repelled from a superconductor, hence the Meissner effect. So everything follows from the Lagrange. Any questions about this?
How did we solve the London equation?
London equation?
Yeah.
This box?
How do we get the solution?
Oh, how we go from here to there?
Yeah.
Yeah, so it's pretty simple. So if you're looking at this situation, the only dependence is x direction. I focus on x direction.
Then it becomes the Irish equation.
Then there may be some sign mistake here. Yeah, I think there's a sign mistake. I apologize.
There should be minus 2e instead of 2e, the right hand side.
Okay, so this was correct. Thank you, Chen. This was correct. But in here, there's a minus sign over here. So there was an over minus sign up here. So that's how you get this equation. Then I can put plus sign on both sides. The derivative squared gives you a number. So if you have this exponential form, the derivative squared just pulls out 1 over this lambda L squared. And that's how you know that this actually solves this equation.
Is that just an isotonic? Is that a word?
This is just a constant, right? Mu naught
Yeah, I
is.
know it's a constant because in 137b we've just learned that this is just the Airy equation, right? I think. Airy equation, A-I-R-Y.
Airy equation, yeah.
Yeah, I think it's just that, and it has the accurate solution is a series, and this exponential solution is just a special case of that function.
No, area is actually, this is linear in distance. So area function is something you get with, for example, the gravitational field, and so the Schrödinger equation. So you have
Oh, right, yeah.
something like this.
All right.
So this is not the same equation for the area function.
So
It is
the
really
variable
constant.
should be, yeah, then the coefficient should be a space-dependent
Right.
variable. Okay.
So here, second derivative just gives you a constant, and therefore you can solve the equation this way, and this lambda L squared is just the inverse of this thing. And this is what is called the London penetration theorem. And now we'd like to talk about this magnetic field squeezed into a narrow tube. So that's actually the same thing as the vortex we talked about for a Bose-Einstein condenser. So idea is to once again solve the Euler-Lagrange equation. And with the boundary condition that psi looks like e to the I theta as a function of this angle theta. When you go to long distances. So its phase circles around once when you go around the spatial infinity. And that's the case you looked at before. For example, the current flowing in a donut shape. You found a solution which changes phase by integer time, L. The same idea. So that's the solution we are looking for. But we also make sure that energy of this configuration is finite, which means that the kinetic energy term so if I actually go back to Lagrange, this is the Hamiltonian. And in order for this configuration to have a finite energy, this combination of derivative and vector potential has to go to 0 when you go to the infinity space. But this derivative will pull out dependence on theta, r del theta, which is supposed to cancel with this one. So A, 1 over R. Should also be like H over 2E, 1 over R. And the total magnetic field in this system is B, area integral, by using Stokes' theorem, that's a line integral. And dr in 1 over r cancels. And if you integrate over for super, you get 2 pi. 2 pi h bar is the original Planck constant h. So you find that magnetic field punching through this system is actually quantized in h over 2e. And this is what I have shown you from distance last time, but this time I pointed out so you can look at it. You should also look at the back side of it, where you see a bunch of these tubes actually moving around. So these tubes, if you have a three-dimensional bulk system, it's kind of heavy, it doesn't move much. But if you create a thin film of superconductor, then magnetic field punching through the system is all actually alive. And if you look at this link and watch the video, you see all these tiny magnetic tubes moving around, flowing. It looks kind of really fascinating. But the point here is that every magnetic field will be quantized in a unit of this unit, h over 2e, punches through the system. You see that the vector potential is really localized in one area. So that's why it means to be squeezed. And inside this tube, you can also see the solution, the psi goes to 0. So condensate disappears. So inside the tube, you lose superconductivity. But outside the tube, it is still superconductor. And because of this London penetration depth, it extends only by a finite distance, and that's why everything is squeezed into this tube of the magnetic field. And outside this tube, as you can imagine from this picture, here's the magnetic field, and this magnetic field is supported by a supercurrent running around it. And that's why you learn electromagnetism. If you have a electric current going in the loop, you find magnetic field going through it. So that's how this satisfies the Maxwell's equation. So everything is consistent that way. You find these magnetic tubes. So that's why if you have a piece of superconductor, and if you apply magnetic field, mostly it gets repelled, but part of it punches through it like this, and you may have many of these tubes, and you can see in the handout that they actually end up forming a beautiful triangular lattice, and magnetic fields is pinned into these flux tubes. So this basically looks like you have a yoke you might use in a grill punching through a piece of meat. Then the meat doesn't turn around very easily on a piece of pork, right? So it looks something like that. And that's how, if you have a permanent magnet and place the piece of superconductor on top of it, it floats. And that's probably something you have done in the laboratory experiment. And this is the idea of how you can actually even let an entire train floating above the rail, and that's the maglev. You can float the entire train supported by this property of the superconductor, and that's how the train can run at a speed of like 400 miles an hour, but it doesn't shake very much because it's not sitting on a rail. And there was one in Shanghai, I understand. I'd like to try that out at some point.
Sir,
Yes.
that should be the flux of the magnetic field.
This is the flux of magnetic field.
So it generally doesn't mean that the magnetic field is quantized, it just means the flux is quantized.
Yeah, flux is quantized. So I should have written P here.
That should be a fire.
Fine, thank you.
And there is no square over the ds.
Sorry?
There is no square over the ds.
Okay, thank you.
Ah.
So this is area already. You're right. Yes?
I'm kind of confused why the fact that lights quantized leads to the fact that there are cubes.
So when you look at this piece here, and looking at the solution, which I did numerically, psi looks like this. So here you lose the condensate, it's not superconductor in the middle, but you recover superconductivity over there, and the magnetic field, on the other hand, looks like this. It's really concentrated over here, and again, dumps exponentially by the London penetration depth once you recover superconductor away from this magnetic field.
Away from what?
Away from this magnetic field.
Okay.
So this magnetic field also follows this London equation, so it has to dump exponentially into the superconductor. That's why it is really squeezed into a small tube. Okay? And also that this quantization goes with 2E instead of E, and that's a demonstration that it is really described by the Cooper pair instead of individual electron. So by measuring the magnetic flux of this situation up there, then you can tell that you are dealing with a condensate of charge 2E instead of E, and that's how you experimentally prove that we are dealing with Cooper pairs, not individual electrons. Okay, any questions about this? Okay, good. And because I have to finish in 2 minutes, I don't move into the next subject, but instead talk about something totally peripheral to this. So what we have learned is that magnetic field would penetrate only by a finite amount in exponential damping. So magnetic field is not short ranged. And if you ever heard of the Higgs boson, this is the same thing. The reason why we are looking for Higgs boson is because we want to understand why you guys can exist. You are made of atoms. You have electrons going around it. And we know electron has a mass and moves with the finite speed much slower than the speed of light. But it turns out, if our universe is really empty, the ground state universe is actually vacuum, then electrons start moving with speed of light, then you would evaporate in about a nanosecond. Something is keeping you together. Electron actually wants to go with speed of light, but something is slowing down. The way that happens is that there is some condensate in a universe which couples to electron field, which gives you a rest energy, namely ME. And this condensate is the Higgs boson. We also know that when you consider, for example, nuclear beta decay, neutron changes to proton by emitting electron and electron antineutrino. But what's going on here, if you look very closely, is that there is actually an interaction of quarks up, down, the down quark in neutron, and down quark changes to up quark, so that becomes a proton by emitting a particle called the W boson, which then turns into electron and neutrino. And this W boson is very heavy. It doesn't move very much. This is what is called the weak interaction. Just like the strong force we talked about before, this is the weak force. This is again a proper noun. We are not very creative. And this is called the weak force because this force is very weak. And it's very weak because it doesn't go over much distance. This is a short range force. But as far as we know, the nature of this W boson is pretty much exactly the same as the photon. And so the electromagnetic field and this W field is basically the same thing, but this one doesn't go very much, only within 10 to minus 16 centimeters or so, while we know electromagnetism go over long distance. So how do we reconcile that? And the idea turned out to be is that our universe is filled with the Higgs boson condensate. And Higgs boson is charged under this W field in the same way that the Cooper pair field is charged under electromagnetism. And the condensate of Cooper pair made the magnetic field short-ranged. In the same way, our universe is filled with the Higgs boson, which is charged under this W field, so that would make this W force short-ranged. And that's how this weak interaction is weak. So if there weren't for the Higgs boson filling up the entire universe today, first of all, you would evaporate in nanoseconds. And second, and in addition, this kind of the reaction of the nuclear beta decay goes much faster because this force becomes long range, and the whole world becomes radioactive. So either way, you can't live. So you exist thanks to the Higgs boson right here, stuck everywhere in space. So our universe is vacuum, but it's not the vacuum in the ordinary sense. It is the ground state of subatomic Newtonian, which shows the condensate of this Higgs boson. And that's many people in our department worked very hard at the Large Hadron Collider and eventually discovered this particle. So it really does exist. So it turns out that QFT is the same language describing superconductor in the laboratory in the entire universe, using the same idea that the condensate or something charged would make the force short-ranged. And that's how we can understand this phenomenon. Okay, that's it. Any questions? Silence. Okay. and I hope you good luck with the meeting. I hope it's going well.
What did you say?
Hello?